Hello everybody, welcome into another lesson. So today we are going to talk about geometric series. Now, just like geometric sequences, these still have a common ratio and the first term, and you first need to set up your sequence. But geometric series, we split into two types. You have the finite series, which will be the first type, and then you even have infinite series, where if you have the right common ratio, you can still get a finite answer. But for a finite series, to find the sum of the finite geometric series, you're going to take your first term times the quantity of 1 minus r, that common ratio, to the n, depending upon how many terms you have, and divide that by 1 minus your common ratio. So the first thing you need to do is determine your common ratio, which we have here with this 5 plus 15 plus 45 plus it skips all the way to 3,645. We determined the common ratio to be 3. We determined our first term to be 5. First thing you want to do is set up your sequence. So a sub n is going to be equal to that a sub 1, which is 5, times your common ratio of 3 to the n minus 1 power. That's the nth term of the sequence. Now, here's the thing. This time we don't actually know the n. So we know the very last term is 3,645. That, of course, is going to equal 5 times 3 to the n minus 1. It gets a little hairy trying to solve for n, because we're going to need to know that to find the sum of this finite series. Well, first thing I'm going to suggest we do is get that 3 to the n minus 1 by itself, divide both sides by 5, you'll end up getting 3 to the n minus 1 is equal to 729. Alright, now we can take a natural log and try to solve for n, but we know 729 is 3 to some power. I'm pretty sure it's to the 6th power. 729 is equal to 3 to the 6th. So 3 to the n minus 1 equals 3 to the 6th. Since we have the same base, we can actually go ahead now and just set the n minus 1 equal to 6. This will save us from having to use a logarithm, which I don't think anyone wants to have to use. That means there are 7 terms. So we now have 7 terms. We know that. There are 7 terms in this particular series. Now that we know the common ratio, the first term, and the number of terms in the series, we can solve for this finite series. So the sum from n equals 1 to 7, since there are 7 terms, of this sequence of 5 times 3 to the n minus 1, we can write that as s sub 7, sum of 7 terms, is going to equal my a sub 1, which is 5, times 1 minus my common ratio of 3 to the 7th, all over 1 minus 3, which is my common ratio. So that's going to equal 5 times 1 minus 729. No, 3 to the 7th, that's, what the heck is 3 to the 7th? That's not 729, that's even bigger than that. 2,187. So 1 minus 2,187 all over negative 2, which is going to equal 5 times negative 2,186 divided by negative 2, which inside the parentheses, the negatives are going to cancel out, so that's nice. We'll get a positive answer. You would end up getting 5 times 1,093, which should give us 5,465. So the sum of this finite series for 7 terms is going to be 5,465. And I got more. Alright, so what's the next one? Let's see, we have 7 plus 14 plus 28 plus dot 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 plus all the way up to 896. So we have 7 plus 14 plus 28 plus it skips plus to 896. Alright, so we can see that the common ratio between each of these terms is 2, right? So we've identified our common ratio to be 2. We even know the first term is 7. What we don't know are the exact number of terms. But let's start out by setting up the explicit formula for the sequence. So a sub n is going to equal my a sub 1, which is 7, times my common ratio of 2 to the n minus 1 power. Well, we know the final term is 896. That's going to equal 7 times 2 to the n minus 1 power. We definitely want to get that 2 to the n minus 1 by itself, so 2 to the n minus 1 is going to equal 896 divided by 7. Let's go ahead and figure that out. That's going to equal 128. Alright, well 128 is the exact same thing as 2 to the 7th. Now that we have the same bases, we can set that n minus 1 equal to 7, and we can get that there are 8 terms. So the number of terms is going to be 8 terms. So now we also know the number of terms. We can find the sum of this finite geometric series. So the sum of this series from 1 to 8 of this sequence of 7 times 2 to the n minus 1, which can be written as s sub 8 since it's a sum of 8 terms, is going to equal my first term of 7 times the quantity of 1 minus my common ratio of 2 to the 8th power all over 1 minus 2. So we'll have 7 times 1 minus 2 to the 8th, which is 256, all over 1 minus 2. Well, that just gives me 7 times negative 255 all over negative 1, which would end up just giving me 7 times 255. Once I find that answer, I found the sum of this finite geometric series. I get 1,785. So the sum of this finite geometric series is going to be 1,785. All right. Let's do another one like this where we got to put the sequence together. Let's see, we have 15 minus 3 plus 3/5 minus ... plus, actually minus, excuse me, it goes all the way to minus 3 over 625. This is a good one because we also have it alternating between positive and negative. But we do have the same common ratio of -1/5 between each term, between 15 minus 3 plus 3/5 minus ... minus 3 625. The same common ratio of -1/5. So we've identified that. What else? We have the first term being a sub 1, which is 15. What we don't know yet are the number of terms. Well, let's start by setting up the formula for the sequence. So a sub n would equal my a sub 1 being 15 times my common ratio of -1/5 to the n minus 1 power. Well, we know the final term is -3 625. That's going to end up equaling 15 times -1/5 to the n minus 1 power. Alright, well, let's get that -1/5 to the n minus 1 power by itself, which means we have to divide both sides by 15. So -1/5 to the n minus 1 is going to equal -3 625 divided by 15. Let's see what we get here. This is definitely going to be a -1 over 5 times 625. -1 over 3,125. Now, we know 5 goes into 3,125. In fact, I'm pretty sure it's a form of some root of 5. We can take -1/5 to the n minus 1, set that equal to, pretty sure it's 5 to the 5th. Yep, so that would end up being -1 over 3,125 is the same as -1/5 to the 5th power. Since we have the same base, we can just set n minus 1 equal to 5, which means n equals 6. So we have 6 terms in this sequence, which means we're going to take the sum of 6 terms now, since we have found the number of terms. So let's go ahead and find the sum here. Little crooked sigma I was starting to draw. from n equals 1 to 6, since we have 6 terms, of this sequence here of 15 times negative 1/5 to the n minus 1 power, which can be written as s sub 6 since we're doing the sum of 6 terms. Alright, so the formula will put in our a sub 1 being 15 times 1 minus our common ratio of negative 1/5 to the 6th power all over 1 minus negative 1/5 so that's going to give us 15 times, let's see, we need to take that negative 1/5 to the 6th power. This is not going to be pretty. That's going to be 15 times 1 minus 1 over 15,625 all over 1 plus 1/5. This is not going to be nice at all, which would equal 15 times 15,625 minus 1 over 15,625 all over 5 plus 1 over 5 when you simplify the numerator and denominator. That's going to equal 15 times 15,624 over 15,625 all over 6 over 5. This just turned very horrendous very quickly, didn't it? So that's going to equal 15 times, we're going to invert and multiply this complex fraction. You'll have 15,624 over 15,625 times that 5 over 6. We can make this not so bad now. Well, good news is 6 cancels with 15,624. This is going to end up equaling 15 times, in the numerator you'll have 2,604 all over your denominator. We know that 15,625 and 5 will cancel out. That'll be over 3,125. So let's see if 3,125 will divide by 15. Not quite by 15, but we do know 5 goes into it. Let me erase some of this because, man, I'm running out of room. I think you get the idea of what we've had to do with the complex fractions. So that's going to really equal 3 times 2,604 divided by 625, which for a final answer we got 3 times 2,604. That gives you 7,812 all over 625. So that would be the sum of this finite geometric series is going to end up being 7,812 all over 625. Which, let's see about what that would look like decimal wise. That's about 12.4992. So yeah, not a pretty answer, but that's exactly what the answer is to this finite series. Alright, so we've had to set up the sigma notation. Now let's do some where the sigma notation's handed to us. Alright, so we have a finite series here from n equals 1 to 9 of just 2 to the n minus 1. Well, they already gave us the sigma notation, right? What would probably help is if we identify the common ratio. Well, the common ratio, that 2 to the n minus 1, that is your common ratio, which is 2. Your first term, your a sub 1, all you have to do is just put in 1 for your n. You'll get 2 to the 0, which is 1. So a sub 1 equals 1. Now, the number of terms, it's already worked out for us. Above the sigma sign, you have a 9, so we have the sum of 9 terms. So to find the sum of these 9 terms, s sub 9, you'll take your a sub 1, which is 1, which we don't even need to write because 1 times anything is that anything. And so this would just be 1 minus my common ratio of 2 to the 9th power, all over 1 minus my common ratio of 2. Which, let's figure out what the heck 2 to the 9th is. It's not going to be a very pretty number, I do know that. It's 512, so you'll have 1 minus 512 all over 1 minus 2. Well, that's going to give you negative 511 over negative 1, which would just give you positive 511. So in this case, you'll get a sum of positive 511 for these 9 terms. Let me get another marker. That one's starting to fade on me. Alright. Now, what if we change it a bit? We have n equals 1 to 9. This time my common ratio is negative 2, but to the n minus 1 power. We're going to have a common ratio of negative 2. So, we know the common ratio is negative 2, right? With the sigma notation. Now, what about our first term, a sub 1? Well, negative 2 to the 0 power is just 1, so a sub 1 equals 1. The number of terms is 9, as denoted above the sigma sign, so this is already cut out for us, but let's see what the sum goes to this time. The sum of the 9 terms equals my a sub 1, which is 1. We don't even need to write that then. You'll just have 1 minus that negative 2 to the 9th power all over 1 minus negative 2. Let's see what you get then. Well, that would be 1 minus negative 512 all over 1 minus negative 2. Well, that's going to equal 1 plus 512 all over 1 plus 2. which would equal 513 divided by 3, and I would like to say that's going to divide evenly. I think it will, actually. Yes, it does. It's 171. So the sum of this series, in this case, is going to be 171 using the formula we've been given with a common ratio this time of -2. And definitely you could credit the lower answer from the last one where you had pretty much the same problem with a common ratio of +2 that time. You can credit the difference to all the negative terms in between. All right. Now, let's see here. We have the sum from I equals 1 to 6 of 32 times 1/4 to the I minus 1. So we have another geometric series here from I equals 1 to 6 of 32 times 1/4 to the I minus 1. Alright, well, let's first identify our common ratio as given here in the parentheses. The common ratio is 1/4. Our a sub 1 outside the parentheses is going to be 32. The number of terms is given to us above the sigma sign, so we have 6 terms. We can easily find the sum now. The sum of these 6 terms is going to equal my a sub 1, which is 32, times 1 minus my common ratio of 1/4 raised to my n, which is 6, all over 1 minus my common ratio of 1/4. So that's going to equal 32 times 1 minus, let's figure out what 1/4 to the 6th power is. 4 to the 6th, so that's going to be 1 minus 1 over 4096, all over 1 minus 1/4, which is going to equal 32 times 4096 minus 1 over 4096, all over 4 minus 1 over 4, based on simplifying the numerator and denominator, which is going to equal 32 times 4095 over 4096, all over 3/4. Now that we have a complex fraction, let's go ahead and invert and multiply. I'll write that over here. That's going to equal 32 times 4095 all over 4096 times 4/3. And I definitely think the 3's and 4's are going to cancel out. Yep, 4095 divided by 3, so that's going to give me 32 times 1365 all over, and I know 4096 will divide by 4, all over 1024. Now my next question is, does 1024 and 32 divide evenly? They sure do, wow. because 32 squared is 1024, you're actually going to end up then getting 1365 divided by 32. That would end up being the sum of this series. You'd end up getting 1365 divided by 32, which is approximately 42.66, if you're wondering what that is as a decimal. So, alright, now what if we have some where the index of summation does not start at 1? What then? So, for example, let's say I have, this time we're starting at n equals 0 to 20 of 3 times 3 halves to the n. So notice something. We're starting at n equals 0. That's our index of summation to the upper limit being 20. This is still geometric. The reason you don't see an n minus 1 is because if you had n minus 1, you would have 3 halves to the negative first, which generally isn't what you do in a series. So if you're starting at 0, you just take n instead of n minus 1. You basically just treat it the same way as if n were equal to 1. You just always want your first term for your common ratio power to be 0. That's why it just has n. But we know the common ratio is 3 halves. That much is easy. Now, we're not going to find a sub 1, we're going to actually find a sub 0. A sub 0 is our first term since n equals 0. Well, 3 halves to the 0 power is still 1 times 3 is 3. So a sub 0 is 3. And then the number of terms, okay, so 20 minus 0 is 20, but you actually have to count that 0th term. So there's actually 21 terms. So the number of terms is actually going to be 21 since you have an extra term. Okay, so let's now go ahead and find the sum. Instead of a sub 1 for the sum, you can just put in a sub 0. Really, it's the spirit of the same formula. It's always really your first term is what you're putting in. So the sum of this series, in this case the sum of 21 terms, is going to equal my very first term of 3 times 1 minus my common ratio of 3 halves raised to the 21st power, since there's 21 terms, all over 1 minus my common ratio of 3 halves. Well, let's see where that gets me when I start simplifying. That'll be 3 times 1 minus... I'm not looking forward to seeing this one. Let's see, 3 to the 21st. Oh gosh, this is horrible. As I thought it would be. This will be 3 minus 10 billion 460 million 353,203 all over, let's take 2 to the 21st. Yeah, I know that's pretty bad. All over 2,097,152 all over 1 minus 3 halves. Let's see what we can simplify now. Alright, so let's bring this over here. You'll have 3 times 2,097,152 minus that 10,460,353,203 all over 2,097,152 all over 2 minus 3 over 2. Ah, that looks horrible. Let's go ahead and simplify our numerator and denominator. Alright, so for the top numerator, we'll have 3 times negative 10,458,256,051 all over that 2,097,152 all over negative 1/2. Let's see what we get now. We're going to have to invert and multiply, so you'll have 3 times that negative 10,458,256,051 all over that 2,097,152 times 2 over negative 1. Well, the good news is we're done with the negatives. That'll cancel out at least. The negatives will cancel out, and this will divide evenly by 2. So, alright, so 2,097,152 divided by 2. That's going to reduce my denominator down to, we'll have 3 times negative 10,458,000. Actually, it'll be positive because the negatives cancel each other out. So 10,458,256,051 all over, this reduced to 1,000,000 and something, 1,048,576. Let's see what we get now. Let's see if we're lucky enough for 3 to divide out from that. Unfortunately, it doesn't. So, we're going to get a really fun answer here. 3 doesn't go into this, unfortunately. So, what you're going to be left with, we just have to do a straight multiplication. You end up getting 31,374,768,153 all over 1,048,576. That would actually end up being the sum of the first 21 terms of this series. you get 31,374,768,153 all over 1,048,576. Okay. Now, let me change this a bit here. Let's say I'm actually going to keep the same common ratio. You know what? Well, our first term is going to be different even, because I'm going to change the index of summation. Let's say let's say you start at the 11th term. So you're going to take the sum of terms 11 through 20 of this finite geometric series. All right, we know the common ratio is going to be 3/2. We do know that. We can clearly see that. But what's your actual first term? That's actually going to be a sub 11, isn't it? A sub 11 is actually your first term, since that's your index of summation. So that's going to be 3 times 3/2 to the 11th power, which is going to give you 3 times whatever the heck that is. Three to the 11th is 177,147 all over. Now, what is 2 to the 11th? That's just 2,048. What I would like to know is, does 2,048 divide by 3? No, it does not. So we're in for a really fun answer here. So a sub 11 is going to be this numerator times 3. So 177,147 times 3, that's going to be 531,441 all over 2,048. So my 11th term, which is my first term, is actually going to be that 531,441 all over 2,048. That's going to act like my first term for this formula. Now, what I need to identify are how many actual terms are there. Well, if I take 20 minus 11, I get 9, but you actually have to count that 11th term, so you actually get 10 terms then. That means n is going to equal 10. So there are 10 terms in this series. Now we can find the sum. So the sum of 10 terms is going to equal my first term here, which, since we're starting at 11, it's going to be my a sub 11 of 531,441 all over 2,048 times that 1 minus r to the n, so that'd be 1 minus my 3/2 only to the 10th power, since we only got 10 terms, all over 1 minus 3/2. So let's see what the heck we get. We still have this awful mess outside of the parentheses, 531,441 all over 2,048 times 1 minus, let's see what we get for everything to the 10th power. So 3 to the 10th is 59,049 divided by 2 to the 10th. don't drop stuff. What is 2 to the 10th? 1024. All over 1 minus 3 halves. Which is going to then equal 531,441 all over 2,048 times, let's simplify in the, let's get the same denominator in both the numerator and denominator. So times 1,024 minus 59,049 all over 1,024 all over 2 minus 3 over 2, which is going to be fun again. We'll have 531,441 all over 2,048 times whatever the heck we get here. Alright, so 1,024 minus 59,049 gives us negative 58,025 over 1,024 all over negative 1 halves. Alright, we have a complex fraction, so we need to simplify that. So we'll have 531,441 all over 2,048 times that negative 58,025 all over 1,024 times 2 over negative 1. Well, good news is your negatives are going to cancel out. And then you end up getting, the 2 will go into 1,024 512 times. So what you really end up getting then is 531,441 all over 2,048 times 58,025 over 512. Let's see what we get, shall we? Let me erase what we have up here so we can actually write the final answer. I know this is not going to be a nice answer. So 531,441 times 58,025 gives me 30 billion 836,864,025 divided by that 2,048 times 512 divided by 1,048,576. So we got a slightly smaller answer than last time when we took the sum of 21 terms, but it's still very large because we're only taking the sum of larger terms as opposed to adding all the smaller ones to it. So the sum of the terms of the 11th through the 20th term is going to be 30,836,864,025 all over 1,048,576. So that's how you take a finite series in the middle of the series, so to say, not just starting at the first term. This shows you could really take it anywhere. Now that's it for this lesson. We're going to do the infinite series in the next lesson. That's kind of its own topic. And believe it or not, I actually consider the infinite series to be easier. You'll see why in the next lesson. So I hope everyone has a great day. Take care.